Welcome. So we're going to be learning about electrical circuits, and we're going to do it in a slightly different way than we've done some of the other chapters, with more of an experimental hands-on approach, but through some digital simulators. So I'm going to do a very quick walk through chapter 23, just to do a few little practice problems with you, so that you'll have some reference for how to solve some of these. And then there's also a whole bunch of Learn chapter 23 activities. And so we're going to do those to learn how it works. All right. So let's start with chapter 23. We have a library of basic symbols. So first you've got a battery. A battery consists of a variety of long and short lines, one after the other. So the long line is the positive terminal. The short line is the negative terminal. So plus is the long line, negative is the short line, and then it's connected with some straight lines. The straight lines that connect things are wires. So the length of the line doesn't matter. It just means that there's a connection. So you don't have to pay attention to how long the wire is or where it turns. It just means connect this thing to that thing using a conductive material. Zigzag like this is a resistor. A little squiggly inside of a circle is a light bulb. And then anytime there's a T, that means there's a junction. So current could make the turn or current could continue straight, depending. We're going to ignore capacitors because that's not an AP Physics 1. And then a switch is just a line that doesn't connect but could connect. And so you've got a couple dots that show it could connect. All right. So let's take a look at that, thinking this through. The big thing with circuits is layout doesn't matter. All that matters is connections. So which of these diagrams represents the same circuit? So I'm going to trace them and talk through the connections. Okay. So in this one, I have from the positive terminal, I come to a junction and I could either go through a capacitor and then back to the negative terminal, or I could go through a resistor and then back to the negative terminal. So those are my two options. These are parallel circuits, one with a capacitor, one with a resistor, both going to the battery. All right, so that's A. B, positive, I could go through a resistor and back to the negative, or I could go through a capacitor and back to the negative. That is exactly the same as that one. So those two are equal. A and B are the same. C, I go from the positive through a resistor, and then I could either go back to the negative. So far it's the same. Or I could go from the positive through the resistor and then through a capacitor and then back to the negative. Now that's not the same. The only way for me to get to the capacitor from the positive terminal is to go through that resistor. And all these other ones, I could go straight to the capacitor and then back to the battery. So this one is not the same. C does not appear to be the same as A and B. And then D, positive terminal, I could either go this way and go through a capacitor and back to the negative, or I could go the other way from the positive through a resistor and then back to the negative. And just to reference, my resistor color was blue. So here's what it would look like on the resistor part there, check. And here's what it would look like on the resistor part over here, check. So these three are all the same. They are parallel circuits with a resistor and a capacitor, both off the battery. So A, B, and D are all the same circuit. Different shapes, different layouts, but the same idea. C is not the same because you have to go through the resistor to get to the capacitor. The resistor and the capacitor are in series, not in parallel. Okay, next one. What is the potential difference across resistor R? So I'm looking for the potential difference, and that would be the voltage, right, across R. I have a current. I have a voltage on the battery. I have a resistor on that one. So I could determine, let's see. Well, I know that voltage V equals IR, current times resistor. So I have 1 amp here. So if I'm solving for the voltage on that guy, since that's a known resistance, I could say voltage equals 1 amp times 6 ohms, which is equal to 6 volts. So this one at 6 ohms has 6 volts. Now I have 10 volts to start with. I lose 6 of them right here. So how many are left? Well, 10 volts minus 6 volts leaves me with 4 volts. So it must be 4 volts on that resistor, and that would be there, negative 4 volts, because this one was plus 10 minus 6 minus 4. All right. So let's look at two different types of circuits, series and parallel circuits. A series is when things are in a row with each other and the current doesn't have a choice but to go through both of them. So there's only one pathway for the current to go through. In this case, these two bulbs are in series because the current has to go through one in order to go through the other one, right? It doesn't have a choice on which way it's going. They're in a run. They're in a series right across. Parallel means the current can choose. So in this case, in the parallel case, I could come out of here as the current, and I could say, I'm going to go this way, and I go through one obstacle, and then I go back to the negative. Or I could come out of here, I could go this way and say, I'm not going to make that turn, I'm going to go straight, and then I'm going to go through this obstacle, and then I'm going to head back to the negative terminal. So that is two pathways, and the current doesn't have to go through both of them. It could go through one or the other. So I have a row here or a row here. That means they are parallel circuits to each other. And obviously the current doesn't have free will. It's not choosing. It's just going through either this run or this run. So I would think like series would be like a series of hurdles along one lane of the track. Parallel would be like lanes on the track. So I can't be in lane 1 and lane 8 on the track. I have to choose either lane 1 on the track or lane 8. But if I'm in lane 1, I have to go through all of the hurdles in lane 1. So the hurdles would be series, the lanes of the track would be parallel. Okay, if I'm calculating the total resistance in series, total resistance is just the sum of all of the resistances. So resistance 1 plus resistance 2 plus resistance 3, add them all together, and that gives me my total resistance for the series. In parallel, take the inverse. So 1 over the total resistance is equal to 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3. The key thing to do at the end is after you do those inverse over resistance, remember to flip it back up so you get resistance total on the top. All right, let's stop and think. Rank in order from brightest to dimmest the identical bulbs A to D. Okay, so turns out when things are in series, or sorry, in parallel, they have less resistance because I'm doing an inverse of their resistance. So things in parallel are going to have less resistance, and that's going to mean more current, and they're going to be brighter. So C and D are going to be brighter, and they're going to be equally bright to each other because when the current is coming through, it's going to go through this one or it's going to go through this one. They're both going to get the same brightness as if they were just a single bulb. So brightest to dimmest, C and D are the brightest, and those are brighter than A and B are also going to be equal because A and B are on the same series track. So parallel bulbs are brighter than series bulbs. Parallel bulbs are equal to each other. Series bulbs are also equal to each other, assuming they are identical bulbs. 23.4. Which is the right way to connect the meters to measure the potential difference across and the current through the resistor? Okay, so this is just how to use a voltmeter and an ammeter. The voltmeter is the tool that's used to measure voltage or potential difference. The ammeter is the tool that's used to measure current. We use the ammeter. Ammeter is current, and that is used in line. So in line means it goes in the circuit. The voltmeter measures voltage or potential difference, and that's used across the resistor or across the obstacle or across the component. Okay, so I need one that has the voltage going, the voltmeter going across the component around it, the ammeter going in line with the circuit. And that one, ammeter is in line, voltmeter is across the resistor. So this is my guy, C. If I look at the other ones, over here, the voltmeter is correctly placed across, but the ammeter is not. The ammeter needs to be in the circuit over here or here or here. In this next one, part B, the ammeter is now in the correct place. It's in the circuit, but the voltmeter isn't across anything, so it would measure 0. It's not doing anything there. C has it all correct, and D has them flip-flopped, so that one doesn't work either. And then last one, a little slightly trickier one, rank in order from brightest to dimmest, the identical bulbs A to D. Okay, so let's think about the current. The current starts in the positive terminal, and it's all going to come out, and it's all going to go through A. So all the current goes through A. Then it has a choice. It can either go through B, or it can go through C and D. Now, C and D have twice the resistance because there are 2 obstacles, right? Think of you running around a track. Would you rather jump over 2 hurdles or just go on the pathway with 1 hurdle? 1 hurdle will be easier, so go that way. More people are going to go that way. Some people will still go the 2 hurdles, so there's more traffic on B, for example. But most people are going to go this way, so you're going to get more current there. So A will be the brightest because it has all the current going there. Okay, so A is going to be the brightest. Then B is going to be the next brightest because it's not in series. So B. And then C and D are going to be the dimmest because there are 2 obstacles in a row, so less current goes that way, C and D, but they'll be equal to each other. And then all the current comes back together and goes out through the negative. Now, you might also think like, well, shouldn't C be brighter and D be less bright because we've used up some of the current there? No, not how it works. Remember, the thing that's actually moving is the electrons, and they're going the opposite way. So technically, the electrons are going this way. They're going through D, through C, and then back through A. But in effect, it doesn't matter. But D, C and D, the current should stay the same through one entire pathway. All right, so there we go. All right, we're going to do some practice questions from chapter 23. Hopefully this all makes sense. If it doesn't, go back and retry some of those chapter 23 learn activities, and they will start making more sense. We are not doing all of the multiples of 5 this time, because there are a lot of multiples of 5 that talk about capacitors, and that is a topic that we do not cover in AP Physics 1. So we're going to skip those, and I assigned a couple extras just to kind of make up for all the ones that we skipped. Enjoy!